Hey, everybody. We're going to look at derivatives of inverse functions. So I'm going to start. We'll do a little review of inverse functions. Remember the basic ideas behind them. Then we'll get to how do we take derivatives of inverse functions, and we'll use that to extend our power rule to rational exponents. And then probably in another video, we'll look at inverse trig functions in particular. So let's get on with the show. So inverse functions, let's just remember what an inverse function is. If we have a function, y equals f of x, its inverse is the function we sometimes notate this way, f, put a little -1 inverse, we say f inverse of x. Or let's say it this way, it's the function that takes the output of f as its input and gives us the original input of f back, right? So this is like our definition. If y equals f of x, f inverse is the function such that f inverse of y equals x. So if we draw a picture, if this is our domain of the function f, and this is the range of the function f, right? So if we pick some point in this function, call this x, then this point, the output, we often call f of x or y. So here's the function f taking us to this new point. Well, then the function, the inverse function just sends us back to where we started, right? So this is f inverse. And this is the point, f inverse of y equals x. That's what this point is, right? It's just two different ways to write that point. So it just undoes the function, right? That's the purpose of an inverse, right? So multiplication by 2 is a function. We can find the inverse by dividing by 2, right? If you add 1 and then divide by 2, you go backwards, you multiply by 2, and then subtract 1, right? So it undoes all the rules. Some functions are more complicated, right? How do you take the inverse sign, right? You have to go through all that process with the unit circle and so on and so forth. But it's still the same basic principle. It undoes it. So this, let's see a couple of properties. For instance, one thing we can say is that f of f inverse of a point just gives us that point back, as does f inverse of f of some point. Just give us that point back, that number, that input, right? Because they undo each other, and that's all in this diagram. If I start at this red dot and I do f, that leads me to this blue dot. Then I do f inverse, it gets me back to where I started. And then if I start at the blue dot and do f inverse, it gets me to the red dot, and then I do f and it gets me back to the blue dot. So if you compose these two functions, you get a function that does nothing. If my function multiplies by 2, then divides by 2, my function does nothing. If it adds 7 and then subtracts 7, it does nothing. So the composition of a function with its inverse doesn't do anything. Now there is something we have to be careful of. Not all functions always have inverses, or they might not have an inverse over their whole domain, which is another way of saying they don't have it, but we can fix it. We're essentially making a new function very closely related to it with an inverse. So let's see why that might happen. All right, let's first look at the function f of x is equal to x cubed. Right, so we probably can quickly decide what's the undoing function here. It's the cube root, right? So f inverse of x will be x to the 1/3. So let's compose these functions. For instance, let's do f inverse of f of 2. So we're doing f inverse. What's f of 2? It's just 2 cubed, which is of course 8. And then the inverse of 8 is the cube root of 8, which is of course 2, right? So we put 2 in, two came back out, no problem, okay? What about the function g of x is equal to x squared? Again, it probably seems like we can quickly come up with the inverse, g inverse. If we're squaring something, we'll take the square root. So let's try that same game. Let's take g inverse of g of 2. So we get g inverse of 2 squared, g inverse of 4, or the 4 to the 1/2 power, or 2, right? The square root of 4. Seems good. 2 went in, 2 came out. But here's our issue. What happens when we try the same game with -2? Well, we get g inverse of -2 squared. G inverse of -2 squared. -2 squared is 4. G inverse of 4 is 4 to the 1/2 power. And again, we get 2. And so we have a problem. We put in -2 and 2 came out, right? The problem, let's illustrate it here. We have our domain of f, or in this case, g. We have our range of g. And there were 2 points over here, 2 and -2. That when we, this is the value 4. So if you do f of 2 and f of -2, you end up at 4 in both cases, right? And that's fine, right? Functions can have that happen where 2 different inputs lead to the same output. What you don't want is that a single input can have more than one output. The inverse function is a function, right? It's an inverse function, but it still is a function in its own right. It has to follow the rules of functions. So to have an inverse here, we need to take the number 4 and send it somewhere. But we can only send it to one place. Our inverse function can only send it to one place. This is a function, and functions take an input and send them to one place, right? But there's 2 choices. Well, I picked one. When I wrote x to the 1/2, that's the positive square root. And so my inverse is going to send the number 4 to the number 2, right? It doesn't care that there was another point to get there. It can only do this thing. And so it doesn't follow the properties we want of an inverse function because it doesn't take any input and send it back to itself, right? As we saw with -2. And in this case, all the negative numbers would have this problem. If we took if we take g of the negative number, we get a positive number, and then we take the square root, we get the positive square root. We could choose the negative square root, but then we have the opposite problem. All the positive numbers don't have this nice returning property, right? This function, x squared, as we typically think about it, does not have an inverse function. It's not what we call injective, or more commonly one-to-one, right? So we assume typically when we write x squared, we're talking about g of x equals x squared with a domain of all real numbers. But when it has a domain of all real numbers, it doesn't have an inverse because of this problem. Let's look at a picture of this. So here's the graph of x squared. The problem, so here I'll illustrate the exact same problem we were just looking at a little differently. Here, the domain, instead of representing it with a blob of a little blob to represent all the numbers, is the x-axis. And the range is the y-axis, right? All the values we can hit lie somewhere on the y-axis. In this case, there are 2 values on the x-axis that both lead to the same output, right? So here's y equals 4. Both x equals -2 and x equals 2 lead us to the same output of 4, right? And so when we take the input, when we take 4 and make it our input, it doesn't know which one to send it back to, right? So this is a graphical representation of not being one-to-one, because there's 2 places that have the same y value. You've probably heard of the horizontal line test. This is our check to see if something is is 1-to-1, it's injective. Okay, and this function is not, right? As we can see, it has more than one place at that value. So if we want this function to have an inverse, we need to fix that problem. And one way that we can typically fix it, let's do this. Both of these up. One way we can fix it is by restricting the domain. So I can take this function g of x equals x squared and give it a restriction. So let's call it something else. I'll call it k of x is equal to x squared, where x has to be non-negative, greater than or equal to 0, right? So this function now is just the right half of that parabola. And now it doesn't have that problem. It only has one input that leads to the output of 4 because there's no -2 in the domain. We can't put that in. And now its inverse is y equals the square root of x because it doesn't have this problem anymore. All right, so that's how we can sometimes get around this inverse, not having an inverse because of a function not being 1-to-1. We have to look at a restricted domain. It's still useful, right? Because if I'm trying to solve problems using this inverse function, I'm aware that there's also these negative numbers, so I can use the inverse, get the positive one, and if I realize I need the negative one, I can deal with that. So it's still very useful, but we have to be careful with it. We see this a lot with the trig functions. The trig functions are incredibly not 1-to-1, right? Every output has an infinite number of inputs that leads to that output because they repeat forever. And so to have an inverse, we have to restrict them to a very small domain relative to their whole domain. So we'll see that a little bit later. So another thing we might notice in this image is there's a nice relationship between these two graphs, right? There's something similar about them. So let's illustrate with a point on each graph. So for instance, here's the point. Oops, let's do, oh yeah, 2, 4. Sorry, that was the right point. Here's the point 2, 4 on our x squared graph. Make it match over the graph. So if the point 2, 4 is on the function, the point 4, 2 has to be on the inverse function, right? Because we know the input 2, if we input 2 into, well, let's just write it here. We know that k of 2 equals 4. K inverse of 4 has to equal 2, right? So for a function, that means we have the input 2 gives us the output 4. Here we have the input 4 gives us the output 2. So we have this kind of, there's a kind of symmetry here, swapping the x and y coordinates, right? So what we say is that this is reflected, a function and its inverse are reflections of each other over the line y equals x, right? And it has to do with this swapping of the inputs and outputs. The domain of the function becomes the range of the inverse, and the range of the original function becomes the domain of the inverse, okay? And to be clear, which one is the function and which one is the inverse is just a matter of perspective, right? I chose k of x equals x squared. K inverse of x is the square root of x. But if I had said, well, let's call L of x the square root of x, then L inverse of x will be x squared with the restriction that x has to be greater than or equal to 0, right? Let's notice something else about that. We have to have that restriction. If we look at the square root of function, the domain here is going to be all positive numbers because we can only put in numbers that are greater than or equal to 0, right, to our square root. And what's the range? The range, it's also only outputting numbers greater than or equal to 0, right? The smallest the square root of something can be is 0 at 0, and then as we get larger numbers, we're getting larger square roots because we're only looking at the positive ones. And in this case, they're the same, but we get this range becomes the domain of the inverse, and the domain becomes the range of the inverse. Okay, and this is true for all inverse functions. Okay, let's look at another couple pictures here. Let's turn this guy off on these points. So here's a cubic function, x cubed minus 1. And here is its inverse, right? Again, we see this symmetry over that line, a reflection over that line, right? If you could, if that red graph was attached to the y equals x line and you imagine spinning it, you could rotate around until you landed on the blue graph, right? That point that's on the line y equals x doesn't go anywhere. That's why they intersect there. And then the other ones swap to the other side. And we see the same relationship with points, right? Here's a point on the inverse, here's a point on the original function. -1, -2 becomes -2, -1. 0, 1, or sorry, 1, 0 becomes 0, 1, right? So we see these relationships holding. Let's look at one more. Here's a rational function. You get the same idea, right? So the blue is the original function. It has two pieces, right? And so if we look at this part of the blue graph, it's reflected in this part of the red graph. And if we look at this part of the blue graph, it's reflected in this part of the red graph. The original function has, for instance, a horizontal asymptote at -2. And so the inverse function has a vertical asymptote at -2, right? And you'll see that at the horizontal and vertical asymptotes will also switch that way. Now, the similarity between these graphs leads us to a thought about the relationship between inverse functions and their derivatives. Okay, so when is a function not differentiable, right? Well, when the limit definition doesn't exist, right? But let's think a little more intuitively for a second. In terms of a graph, when is it not differentiable? We see when it's discontinuous, when it's a jump or a corner, then we end up with places where it's not differentiable, or where it has a vertical tangent because right, we can't get a slope of a vertical line. So if a function is differentiable, it doesn't have any of those things. It doesn't have any jumps. It doesn't have any corners and things like that. The graph of the inverse will be the same, right? And so it shouldn't have any jumps or corners or holes or any of that stuff. If the original function does, then the inverse will as well, but only in the same points, except with that switching of the x and y, right? So if our original function has a problem, like a corner at 2, 4, the inverse will have a corner at 4, 2, okay? So keeping in mind the switching of the domain and range, that our inverse functions will be differentiable where our forward functions, our original functions are, with the exception that if the tangent line to our original function is horizontal, then the tangent line to the inverse function is going to be vertical, just like those asymptotes switched. And so there's a point where if you have a horizontal tangent, you have a differentiable point of your function, the corresponding point to the inverse function won't be differentiable, but it'll still have the same look as our function. It's just that we can't output a slope value for a vertical line. So with that in mind, let's investigate this relationship more clearly. Okay, so let's start with this. We'll take y equals f of x is a differentiable function. Okay, now let's use as a differentiable function with inverse f inverse of x, okay? Let's look at f of f inverse of x. So we know that this puts x back out, right? It spits x back out to us, okay? Let's take derivatives of both sides, right? These should be equivalent functions, right? We wrote equal, so they should be the same thing. So their derivatives should be the same. So the right-hand side, we have no problems. Derivative of x is equal to 1. Let's write that in a second. I'm gonna make sure I have enough room. On the left-hand side, we can use the chain rule. Remember the chain rule. So we take the derivative of the outer function, which I can write as f prime. I leave the inner function alone. And then I take the derivative of the inner function. So I'll write this as d dx f inverse of x. All right, so we're taking this derivative. And then the derivative of x is just 1. Okay. Well, now, remember what I want to do. I want to find out about the derivative of the inverse. I've got the derivative of the inverse sitting right here. It's just being multiplied by this thing. I can divide both sides by that thing. So we get d dx f inverse of x. I didn't need that. Is equal to 1 divided by f prime of x. Sorry, f inverse of x. Okay. So if we want to take the derivative of the inverse function at a point x in the domain of the inverse, we look at the derivative of the original function at the point that led to the output x. So let's try to draw a picture of what's going on here a little bit. So let's say here's my function f, and let's call this, let's do this point here, let's call this AB, and it's got some derivative and a tangent line and a slope given by that derivative. So let's try to draw it. Let's just represent what that might be. Let me move something a little bit. So this is the point AB. And the slope of the tangent line here, right, is going to be represented by, right, that's what slope is. It tells you the rise over the run. So if this rises, I'll just call it, what letters have we not used in a while? Let's call it S and T. So the slope here, in other words, the derivative f prime of A is going to be S over T, right? That's what the derivative at that point does. It tells us the slope of the tangent line. So now let's imagine, so here's, I'm going to draw in the line y equals x. Let's pretend it's right here. And then draw in the reflection, right? So, oops. Something like, whoops, I don't want that. Oh, I'm taking too long and then it turns into these nice pretty curves. So I've got to go near it. Something like that, right? So it's not a perfect drawing. Actually, it's not very good. Let's try one more time. Let's try, put in the point about here. All right, just draw that relevant part, right? So here's going to be this is my F inverse function. If this is the point AB over here, this must be the point BA, right? It takes the out, that's the remember the swapping of the coordinates, right? And the tangent line, right, it's also going to swap in the way in which it's oriented, right? So while this graph, the way I've drawn it, is going has a more horizontal change for some vertical change, it should be the opposite here. We have, my drawing's not perfect, but if you can imagine a more perfect drawing, this horizontal change now should be S, and the vertical change should be T. And so F inverse prime, this is an ugly notation, at the point B will be T over S, the reciprocal of the derivative at the point A. And to finish off the connection here, this point A is equal to F inverse of B, right? That's what being at this point means. So what this theorem is telling us, or what we just discovered here, is that if I want the inverse at a point on the inverse function's graph, I look at the place that had the same output and I say, what's the derivative for that input? And I take the reciprocal. Okay, so it's not super simple, right? And this formula is ugly to look at, but you have to dig through this idea a little bit and see what's happening here. It's this reflection over the line, I think, explains why we end up with this. Note, this also shows that what we had said, that if we have a horizontal tangent line, we can't have the derivative of the inverse there, because then we have a vertical tangent line and there's no slope number we can give to that. And it shows up in this formula. If our original derivative was 0, a horizontal tangent line, we have a 0 in the denominator. And so this breaks down. So let's summarize this with what we call the inverse function theorem. Let f of x be a function that is both invertible and differentiable. This is really just what we started with, right? We said it's differentiable and it has an inverse. So just invertible means invertible just means it has an inverse. Let y equals f inverse of x be the inverse of f at all points such that f prime of y is not equal to 0, right? So f prime of f inverse of x, which is y. So it's just saying it's at all points such that the corresponding point in the original function doesn't have a 0 derivative, doesn't have a tangent line that's horizontal. Then dy dx, or the derivative of the inverse function, is equal to, so you'll also see people write it this way. I kind of hate this notation, but I see it out there. It's sometimes handy. I shouldn't hate it. I use it sometimes. It still bugs me. Is just equal to what we set up here. It's the inverse, it's the derivative of the, it's the derivative of the original function evaluated at I'm going to say the corresponding point on the original function, right? F inverse of y. Okay. Okay, so let's do a quick example of this, and then I was going to use it to prove something. I think I'll save it for another video because this one's getting pretty long. Okay, so let's look back at the function f of x squared. Sorry, f of x equals x squared for x greater than or equal to 0. Let's find the derivative of f inverse of x equal to the positive square root of x at x equals 9. So first, we will find it using this new theorem. Okay, so we want to take the derivative. Sorry, let's do it this way. I'm going to use that notation that I said I hated. F inverse prime of 9 is going to be equal to 1 over f prime of f inverse of 9. Oh, I did write this wrong. Something was bothering me. I felt like I wrote something wrong here. This should be x. Sorry about that. I was going to write just y there, f prime of y, but that's also f inverse of x. Something felt off when I was writing it, but I couldn't see what I was doing. Okay, sorry about that. So here's our formula. Well, what's f inverse of 9? Well, that's just f inverse is the square root of x, so that's f prime of 3. I like my brain or my hands going ahead of my brain today. So now I want f prime of 3. Well, what's f prime? So if f of x is equal to x squared, f prime is 2x. So f prime of 3 is equal to 6. So we get 1/6, right? That's fantastic. There is our derivative of f inverse at 9. But let's check this against the definition of the derivative, right? Let's just take the derivative. I'm gonna write let's just take the derivative of the square root of x. Okay, we don't have the power rule. I haven't proved it yet for rational functions, so let's just take it using the definition. We haven't seen the definition in a while. The limit as h goes to 0, square root of x plus h minus the square root of x all over h. We can multiply this whole thing by the complex or the radical conjugate. So just do that up here, square root of x plus h plus the square root of x, square root of x plus h plus the square root of x, I'm multiplying by 1. So I end up with x plus h minus x over h times the square root of x plus h plus the square root of x. Those x's cancel. I can cancel an h here with an h there, so I'm left with 1 in the numerator, and I've got the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. Now I let that h go to 0. I can just do direct substitution because there's no problem here, and I get 1 over the square root of x plus the square root of x, or 2 square root of x. And now if I want to evaluate this at 3, I get, at 9. We were taking the derivative at 9. I get 1 over 2 square root of 9, 1 over 2 times 3, or 1 over 6. And so it gets us exactly what we expect it to give us, right? So this theorem works as we would expect. Okay, so a couple of things. One, I said we were going to derive the power rule for rational exponents, but let's do that in another one. This one's getting long. It'd be nice to have it segmented. Number two, why is this useful? Well, sometimes it's just easier. Sometimes you don't know the inverse, right? Or you don't have the inverse. And maybe if it's a complicated function, finding the inverse is difficult, right? And so sometimes it's just nice to be able to take the derivative without actually having to know what the inverse is, right? We happen to know it in this case. We're starting with a simple example, but if this was a much more complicated function and we had an interest in knowing some information about the inverse, this is a way we can get it, right? This is a way that we can have access to some information about that function because we have access to its derivative, even if we don't have the ability or the time to compute what that function actually is. Having access to the derivative is pretty important, right? As we're starting to see, and we'll dig into a lot more closely as we go along, the derivative really tells us everything about the behavior of a function, where it goes up, where it goes down, where it's horizontal, all that kind of stuff is captured in the derivative. So we can really pull a lot of information about a function from its derivative. And so having access to the information, even if we don't have the function, is a pretty powerful tool. Okay, that will be it for now. Thanks, everybody. I will see you next time.